Hello YouTube Pixies, Hoofbag here again. There's a little bit of buzz. I mean, obviously everybody knows about like germanium fuzzes and how they sound. Never really impressed me very much. But there's also whole amplifiers made using pretty much obsolete germanium technology. Okay, now this here is a transformer coupled one. It's only 3 stages of amplification, and the transistors are OC81, I think, or maybe 78. I'm not sure. I think they're OC78, and this one's an OC78D, and we've also got an OC71 germanium transistor. It's all 1960s stuff going on here. Now, the other thing to mention is, for whatever reason, companies are asking quite a lot of money for this obsolete technology. This is an LT44. You can look it up on eBay. I think they're going for about 3 or 4 quid each. LT44. So these two usually go together. You buy an LT44, LT700, and you get more or less 2 driver transformer, output transformer for near enough a tenner. Now, do they sound any different from any chip amp or an amplifier made out of silicon transistors? We'll know in a little while. I'm just going to try and play a couple of my riffs and see how we get on. Okay. Try and turn the volume down and see if I can get a clean sound out of it. I must admit that the gain for 3 stages is absolutely astounding. I think the reason why is because the driver transformer and output transformer, what they do is they match the impedances in the circuit perfectly. So normally you'd have more stages of amplification. This is just 3, and it's astonishing how much gain you get with just 3. stages, because of course these two transistors are considered one of the stages, the output stage, and it works in push-pull, class B bias or class AB. Okay, volume level. We're only talking, with the 9-volt battery, we're only talking about 100 milliwatts. The speaker happens to be a high sensitivity one out of an attaché valve radio. I'm sure this is only 100 milliwatts, but the transformers are called LC45 to 700. They're actually 200 milliwatt transformers, but I found that you have to run it at 12 volts in order to get 200 milliwatts out of them, or I don't know, milliwatts in RMS. I don't think it matters. The voltage is the thing that matters. So I suppose I could check it. I don't know if I've got the right equipment. And also, if my playing sounds worse than usual, if that's at all possible, it is absolutely freezing in here in the UK, and of course my fingers are, I just have to get used to being cold because we can't afford to heat our homes, unfortunately. Anyway, let's play on. I just showed you how much matching the stages increases the gain and the efficiency of each stage, especially considering that the OC71, which I think is what it is, it has only an HFE of about 40, probably about 60 to 100 for the OC81D, and the two OC81Ds around about 100. And you would never get that amount of gain out of without using the transformers. Okay, there's another issue in regards to these transformer coupled germanium amplifiers is thermal runaway. Now, one of the problems people used to have in the 1960s when these type of circuits were first developed, transistor radios, people used to find that they buy a new battery, take from a shop, put it to their radio, put it in their radio, and then they would find that if the battery went down by about, say, 10% of its charge, then the radio would sound terrible. Now, one of the reasons for this is because there's a lot of phasing going on in the output stage, if you reduce the bias, it really does have a dramatic effect on these on the actual biasing setup. You see, the battery supplies 9 volts, and the actual base voltage has to be around about 200 millivolts. And what would happen there is if the battery reduced by, say, 20%, you'd have an equal amount on your reduction of bias on your base circuit. Now, the way they got around that is by, there's quite an extensive description of what they call recent developments. And what they would do is replace this potentiometer with a metal rectifier and a resistor across the metal rectifier in parallel with it. Nowadays, we would use, if assuming you want to build one of these, it would use a germanium diode, which will have the same amount, the same effect, same voltage as the base emitter voltage. They'd be both around about 200 millivolts. Okay, I'm being very, very naughty. This is radio and television servicing, 1962 to 1963 models. And this is the original, this is the output stage. Now, we're disregarding the two input stages, or one that we've got here. We're entirely focusing on the output stage. That can be dealt with in a separate video. But the original circuit was like this. So this is the transformer output one. This is the LT44, LT700, LT44. And these would be PMP, and this says NKT251. An OC81 would be a near equivalent to that. So, of course, we've got, this is how, it's a split bias arrangement. We've got the 4.7K providing bias to the transistor base, which goes through the coil, secondary, and then it's got another resistor there. Now, in a later design, they used to use a metal rectifier with a resistor in parallel, just like I said. Now, right, so I'll read some of it, because it's really worth understanding. It is well worth knowing about this. With many transistor, I'm reading text now, okay? With many transistor receivers, the battery has to be discarded because of the increase in crossover distortion as the voltage falls. Now, these particular the actual output stage is very, very tightly coupled. So any slight variation in voltage will have a dramatic effect. I mean, I can't really go into, I don't really know if I fully understand it, but kind of, I've got an image in my head that figures it out, if you know what I mean. The output stage providing low, because the battery voltage falls. An output stage providing low crossover distortion at low battery voltage would normally pass as uneconomically high no signal current with a new battery. Uneconomically high. So in other words, you'd be drawing an awful lot of current through the transistors and they'd warm up a bit. Several different systems have been used to overcome this difficulty and so enable the battery to be retained longer. Examples are the split load output stage, that's something we need to ignore for the moment, and the use of small metal rectifiers in the base bias network. See, for example, the Murphy model, blah, blah, blah. I mean, they're obsolete now. Murphy model B385. Where would you find one of those? I mean, you know, it's ancient history here. This later technique became further developed by the Pi group under the name peak performance control to provide stabilized base bias in a class B output stage. In other words, our LT44, LT700, two OC81s in push-pull, so as to give satisfactory performance over a wide range of battery voltage and ambient temperature. Figure 2 shows how the system has been applied to the Pi model Q8. Here we go. A transistor type NKT259, it will be nearly equivalent to an OC72 or 81, connected as a junction diode between the center tap of the driver transformer and the positive chassis line. These in PNP transistor technology, typical radios, they would have negative as the supply and the positive would be grounded and it would be joined to the chassis. The upper resistor of the base bias network is replaced by a preset resistor which is adjusted to give the correct no signal standing current with new battery voltage. A battery voltage falls and the current through the diode connected transistor falls. Its forward resistance rises, tending to keep the collector current to its original value, so preventing the onset of crossover distortion. Since the stabilizing transistor is affected by temperature variations in a parallel manner to the output transistors, it automatically provides temperature compensation. This is going into the various parts of the radio to do with the RF circuitry. We're only concerned here with the audio stages. So what I might do is connect up. Now we've got a brand new, well, it's a PP3 and it's virtually new, okay? And if I connect it up and alter the bias, have a quick play. Let's check it's still working. I'll turn that down. Right, now I'm going to alter the bias. So in other words, the transistor base voltage will be nearer to positive ground, okay? Right. I mean, I don't like that sound, I'm sorry. Just have a glug of coffee. I mean, to me, there are some fuzz boxes that sound like that to me, and people say they like it, but I couldn't live with that, not personally. So we're going to set the bias to a more reasonable, what I would consider a nice sound. So I've got, this is I think it's a 100 ohm preset skeleton potentiometer preset. Just a little bit of, got some dead areas there. The problem is, we're probably drawing a lot of current at this point, so it's actually gone in that. If you go like that, it'd be class A bias, which you don't want. That should be okay. Yeah, they're cool. Nice and cold. I think the battery voltage is dropping. That's probably why it's sounding a little bit crunchy. Let's give it a check. Stick it on the 20. That's my digital voltmeter. Cheap old thing, but it works. Now what I just did there was I connected the negative to the ground. And I'm doing that all the time because I'm so accustomed to having negative ground, positive supply. So that goes there. It becomes so much of a habit after a while. So then we've got 8.6 volts. Yeah. So what's happened is we've lost about half a volt, which does make a huge difference, oddly enough. Okay. This is my little homemade power supply device, and I'm going to mark it where it says 9 volts. I think I've never done that, and I should. 9 volts there. Okay. Or is it? No, it's 12. Never mind. I'll go over it in a little while. But I can get anything from 3 volts up to say 6. I think it's 15 volts out of this thing. So what we're going to do is set the bias to 0, because otherwise we're going to get too much current flowing through the transistors, and they won't like it very much. They'll get a bit hot. Now still a little bit of crunchiness going on. Now what's happened is that I've actually set the my variable power supply to I think 12 volts. 11.98. Okay. Now, obviously, one of the things they could have done many years ago is have a little knob on the front of their radio, and they could have altered the bias as the battery dies. Okay. Now, one of the problems with that is if you turn it too far, you're going to get a huge amount of current flowing through these transistors, and especially as they're about about a day's wage. They're so expensive, transistors in those days, and they are now again. I mean, you look up the price of an OC81D, you're talking about, some people are taking the piss. They're charging 30 quid for it. So we know that we've got a voltage there, which is important. So now we're still getting that crunchiness that I don't want. So we're gonna bring up the bias. one of the reasons why I chose this meter by Alti. It's quite a cheap one, or Metex or something by Alti, okay, is it happens to have an AC voltage range that goes down really low. So if I hit a chord, I'm getting 1.3 volts. Let's switch this off a moment. So this is how you do wattage. If you can get a reading of the output of an amplifier in AC volts, or AC volts on your voltmeter range, assuming your digital meter goes down that far, what you do is it's V squared divided by R. So do 1.2, right, times 1.2, or squared, equals 1.44, right? So we divide by 3 ohms, divided by 3 equals 0.48 of a watt. That's half a watt at 12 volts. Now here's another experiment concerning the same little amplifier. Okay, this is a germanium diode, and I presume it's got the same. Normally all germanium devices 0.2 volts forward bias. So I'm going to take this off, this potentiometer, to as they said in the book, they used a metal rectifier with a resistor across it. Now obviously the current is going in this direction, okay, from positive it's going up. So if you look at a diode, it's like let's draw it there. It's got like that and like that, with that going across like that. Now that arrow there signifies the direction of the conventional current. Obviously that is opposite to electron flow, but it's important that we connect this the correct way around. So I'm just about to do that, and let's see what happens. It should just be at 0.2 volts, as one would imagine. If it was an NPN circuit, we would have to put the diode the opposite way around. Aha! Got a short circuit there. Now what's happening there is the diode in forward bias is setting the voltage exactly as it needs to be at the junction of the base of the transistor, which is there. Obviously we have to disregard the small resistance of the coils, but those 3 points there, base 1, center tap of the driver transformer, and base 2 are all at the same potential, apart from say 0.01 of a volt or something like that. Right, now according to the book, if I reduce the voltage if I reduce the voltage, which is the same thing as a battery getting near to expiry, we won't get that same crunchy effect. We'll get a reasonably clean tone. So I'm going to set the reduce the voltage. That sounds nice. Take it down a bit further. Now, if you were trying to use a fixed resistor or this potentiometer, you wouldn't get anything like as nice a sound as that. Be interesting to know what voltage we've got at this point. Right, we're down to 5 volts. So you can imagine then that when they used to buy their batteries, and I remember my mum used to, the battery used to get terrible state, and she'd have to, oh God, got to buy a new battery for the transistor radio in the kitchen, and they weren't cheap. So we're down to, well, look at that, we're down to, I'm using my analog meter there, which is this one. Alright, so we're down to probably about 2 volts. See how much further we go down. Right, we're down to 1 volt now. So of course, poor old housewife like my mum, for example, in the 1960s, you know, I think maybe her radios did have this voltage reference system built into it, but you do get to the point where you know, the battery voltage, usually a PP9 for example, would be so incredibly low that well, it would just not, you wouldn't hear it. It wouldn't work anymore, and they'd be forced to go out and buy a battery. Now, it's an unfortunate thing that my dad was an electronics engineer, but he couldn't really be bothered to help my mum very much. And what he could have done is got himself a what we used to call a power pack, and you get a transformer and a rectifier, and set it to 9 volts. I suppose it would have been a bit of a job because you would have had to take out the windings. So it's 1 volt, 1.3 volts, and still working. Incredible. So what's the next thing to do? Oh, to show the various transformers. Now this is, I think, I don't know which one's which, but I get the impression, yeah, it's got 2 thick wires coming out this end, 2 very thick wires, and you wouldn't read anything at all on the resistance. And this is where the collector of the OC81 will go. Collector of the OC81 on the other side will go, because you've got 2 of them, and that will be the supply. And this here is the driver transformer. This middle connection will be there, and these 2 outer ones will be there and there on the base, and we've got 2 for these 2. So these transformers and the output power of an amplifier built in this way is heavily dependent on the voltage and the size of the transformers. Probably get about 3 watts out of the output one, definitely. Now, one of the problems with, as I said, the minimum bias is a problem with these, or a fixed resistor, but also the maximum bias current would be a problem because the transistors, and they're very expensive in those days, and they've gone up again because they're rare, these will get really hot. And it's the last thing you want, because once there is something called, a common thing in transistor technology known as thermal runaway. So of course, if you try to apply too high voltage and you had the fixed bias without the diode setting the voltage, then you would burn the transistors out, and it will be a very expensive repair. Let's see how far we can go and see how loud this thing gets. One way of checking the the volume level of this thing is if I try and sing with it, you know. So this is a germanium transistor amplifier. This is a germanium transistor amplifier, because germanium rocks. Germanium rocks. I'm gonna let's have a look to see how they're doing. Yeah, they're getting a little bit warm, but be interesting to see what we get out of it at this voltage. Where are we? So we need to disconnect. So we're going to try and set the 2-volt level in AC, and I mean the voltage is about, I think, 15. Let's check that using this. All right, 10 volts. So what we got on the HT? Right, it's 15 volts. Okay. So at 15 volts, a amplifier of this description will give out there isn't actually that much of an improvement, to be honest, so I think it's best to set it at around about 12. And it's a common misconception that if you increase the voltage of amplifier you get more out of it. It doesn't necessarily work that way. So I think we've covered everything. So what we're going to do next time, fairly soon, is we're going to construct a Class B output stage using LT44, LT700 and OC81s, and going to go through step-by-step instructions on how to build it if you happen to be so inclined. Now, I should also point out that for the price of one of these, like, you know, transformers, you could probably get 2 or 3 LM386s and they'll give out more. So you would have to be particularly dedicated and wanting a germanium amplifier, you know, badly enough to commit yourself to the expense. And I mean, obviously it'd be worth knowing how much OC81s are set an exactly HFE matched pair. That's why they've got yellow dots on, you see, because they're a matched pair. And the OC81s are extremely expensive because they're used in fuzz boxes. OC71s you can get, but in addition to that, there's also a supplier on eBay of PNP germanium transistors from Soviet Union or Russia or wherever, and that might be worth trying and see what we get out of it. Anyway, in the meantime, thank you for watching. Bye.